Good morning, everybody, and welcome to another lecture of our Calculus for Life Sciences course. All right. So previously we talked about the basic quadratic function, and we also introduced some basic function transformations. Let's go over them now. I think I just have to increase my pen size here. This doesn't look right. Man, I'm all over the place today. Black. Can I get a black pen? There we go. Ah, that looks better. All right. Review from yesterday. Function and therefore graph as a result. Transformations. Alrighty. Okay. So of course you can technically do these transformations in any order. Some, however, will be more convenient to do first and some more convenient to do last. If I have my basic function, I'll just do them in this order. I won't number them. And I change it to y equals some positive constant a times f of x. Now, what helps me remember is the right-hand side stays the same, but gets multiplied by a positive number. Then the resulting graph undergoes vertical, I want to emphasize, vertical stretch or compression depending on the size of A. But if something is done to the whole right-hand side, then some vertical transformation is happening to the graph. Next, and these can be shuffled around. If I have some function, it could be y equals x squared, but it's not limited to that. And I multiply the whole right-hand side by -1. Again, that's a vertical effect on the graph. It's a vertical reflection, I'll call it. It's a little bit confusing to some people, perhaps. If I call it a reflection in the x-axis, then you focus on the x-axis, which is horizontal. So I'll just call it a vertical reflection. Then I can imagine flipping it vertically. So that might be an easier word to use. Then we can also do a very different transformation by replacing x wherever I see it with an x, let's call it minus p. Could be a number, x plus or minus, depending on what p is. That is a replacement. And whenever I do a replacement transformation on the function, the graph effect is going to be a horizontal. In this case, I'll call it a shift, horizontal shift. Fancy word is translation. Doesn't matter. It's moving horizontally. The shape is the same. We're just shifting it horizontally. And the one that I find is the safest to leave to the end, these can all be flipped around, these first three. I find it a little bit safer if I leave this transformation to the end. So I keep the right-hand side, and I'm going to add or subtract, depending on the value of q, but a number. Again, something is done to the whole right-hand side, so that means a vertical transformation is happening to the graph, vertical shift. So there's some consistency between these. If the whole right-hand side is being manipulated, then it's a vertical transformation to the graph. And when x is being replaced by x plus or minus a number, then it's a horizontal shift. Now there's one more we're going to add eventually, but not right now because the quadratic function doesn't really need it. These are the 4 we have right now. And we want to keep this as simple as possible. There are more. We don't necessarily need to see more. I want to do a problem. Oopsie. Let's see here which problem. I want to do 1.6 number 4. Problem 1.6 number 4. And of course that all refers to the problem book, which we'll use as in-class examples. Number 4. So I ultimately have to graph and figure out f of x, -2. So we're given f of x, -2x plus 1 squared. And then we have a plus 4. All right. Now it says here, do it by way of a sequence of transformations. And I'm going to talk about standard form in a second, and then we'll identify what happens to the vertex as we keep track of it, axis of symmetry as we flip and shift this basic graph, and then that'll be that. So I want to make a sequence of transformations. So I want to make a sequence of transformations. And of course, I'm building, let's make the sequence first. Sequence, whoopsie, that got away from me. Sequence of transformations. Remember, the function comes first. And then each time I make a transformation in the function, the graph of the original changes as well. So let's just get a plan here. Of course, I'm going to start with my x² function, which this is built on. Then I'm going to change it to 2x², which is my preferred first one. Then I'm going to change it to -2x². And I separate the negative from the 2 always because it's a different effect on the graph. Then I'm going to change it to -2x plus 1 squared, which is a replacement of x. And lastly, we're going to change it to the end result by taking that previous right-hand side and adding 4. So we have a few steps in our sequence of transformations. Each one will have a graph. Now, just to keep things simple, I'm going to just erase these bottom 2 and then have space for the graphs right in line. Can I erase all of it before it runs out of memory? So close. So close. Let's manually get rid of that guy there. And the arrow needs to go. All right. Now let's set up some XY axes here. And then we'll do the last 2 in that sequence underneath. So we're not going to have very big fancy graphs, just a rough sketch here, as long as the shape of the original is preserved. So, of course, I start with my basic parabola. I'm going to make it nice and wide because I know the 2x² is going to stretch this, making it a little bit thinner. Trying my best at a nice curve here. And of course, that bottom is the vertex at 0. Let's keep track of another point. Whenever I need to stretch or compress it, it's nice to indicate that I actually did change the graph, because sometimes my shape doesn't show the stretch as effectively as I'd like. I don't want to make this parabola super thin. It's difficult for me to draw. So I'm going to make it a little thinner, but I'm not going to make it as thin as it actually is when x and y are the same scale. It's hard to draw those. So I help by keeping track of my vertex, of course, and then showing that the point that I indicated previously is now at 1, 2. So I did do something. Next, I take that whole right-hand side and I multiply it by -1, which flips everything vertically. So now everything is just upside down, trying to be as neat as I can be, but of course it's not an art class. As long as we have the curvature and the symmetry and have a nice round at the top, those things are the key properties, right? And we don't wobble like this, then those things are not properties of the graph. And my point now sits, my extra reference point now sits at 1, -2. All right, so far, so good. And then we said, we'll take it down here to replace x with x, what was it? plus 1. Plus 1. Let's set that up. I have this space so we can make them a little bigger. So now it's replacing x with x plus 1. So that means that it's a horizontal shift to which side? Who can tell me to which side it shifts horizontally? Left. Perfect. How you remember it? I remember I had to just sort of make a note that it's counterintuitive for me. So plus here actually means left. All right. So now it's only left by 1. So my vertex maybe sits over here now at -1. And I'm going to have this axis of symmetry line that was sitting on the y-axis now shifts and becomes something visible maybe. Well, not visible, I can make a dotted line just to help myself, but I want to indicate that. And now I can draw my parabola. This one is not the greatest parabola I've ever done, but I'm just going to go with it. A little wobbly here, right? My point that I kept track of is now sitting right on the y-axis because I shifted by 1. So I get the y-intercept as a bonus, but I can also calculate it at the end. We'll make a note of that. And then we have one more step this way to finish it by adding 4 to the whole right-hand side, which means it's a vertical effect on the graph. Give ourselves some space here. Axis of symmetry sat over here somewhere at -1. We had our vertex on the x-axis, which means at 0 for y. That now shifts up 4. So let's put it really nice and high. Let's put it up here. 4 is quite a lot. My y-intercept was the point that I kept track of, and that was at -2. Now it shifts up to 2. Now, instead of making a point and trying to curve right through that, I'm just going to make a nice parabola shape, trying to go halfway. It doesn't have to be perfect. And then I will say, well, the y-axis scale is what it needs to be for that to be a 2. The shape, the curvature is more important than the scale on your axis, which is why I don't want to use grid paper and sort of feel restricted. If you use grid paper or graph paper to graph this, the parabolas are actually very narrow and not easy to draw at all. So I just say, let the scale be what it needs to be to create this parabola wide shape. Because it doesn't matter. It's just moving the graph around and visualizing that in the nicest way. The preciseness of our scale isn't quite the point here. All right, so there we go. that is it. Now there's a little more to the question. The y-intercept was right there. We'll just indicate that. Y-intercept is at 0, 2, because we got it sort of for free. And if we didn't get it for free, then we can always set x equal to 0, calculate the answer. In this case, it's a 2. They also want to know the x-intercept. So let's see if we can squeeze that in somewhere. I think we can do it over here. X-intercept, or in this case, oops, it looks as if we'll have 2 of them. I can, from the graph, read where they are, right? That's too hard. I can't trust my graph that much. So I set y equal to 0 and solve the equation that I get. I'll flip the equation around a little bit. I'll do it over here. Negative 2x plus 1 squared plus 4 equals 0. I like my stuff on the left. Let's zoom in on this. Oh, I can't really zoom in, to be honest. Maybe a little. That might be too much zooming. Too much zooming scares me. Oh no, I'm not even on the webcam anymore. What happened? Polar bear decided, nope, had enough. This is nonsense. I'm out. Where are you, polar bear? I miss you. All right, x-intercept. I got distracted. I apologize. So now I have negative 2x plus 1 squared equal to negative 4. So x plus 1 squared equals negative 4 divided by negative 2, which is 2. So x plus 1 is then the square root, but plus or minus root 2. And finally, x is negative 1 plus or minus root 2. Calculate the decimals, do what you want to do. It'll be these guys over here. Okay, so if I have it in this, what we call standard form, great. It's not that hard to calculate the x-intercept. What else do they ask me? Sequence, vertex, axis of symmetry. Sure, let's indicate here. Let's do it over there. I'm running out of space. I didn't plan this very well. Axis of symmetry is a line. It's a straight line. It's sitting at negative 1. It's the vertical line x equal to negative 1. What else do we have here? Is the vertex yielding a maximum or a minimum? Clearly, the vertex is the point negative 1, 4, and it yields a maximum because it's the highest y value that I can get. Okay, so by looking at the parabola, we see some features of the quadratic function, axis of symmetry, vertex, maximum, minimum. We can find the intercepts. Good to know. All right. Let me see. Can I go back to this page? I've got a lot of space here. So let's just note we have our standard form for our quadratic function, which looks like this. Now in this case, don't be confused. In this case, in the standard form, this a may contain negative 1. It's merged into it, so it may be negative. When I do my transformations, then I can see the actual number and I separate the negative 1 from the size of the number, so don't be confused by that. We can find our axis of symmetry. When I have it in standard form, the axis of symmetry is very clear the line x equal to p. The vertex is the point PQ. Sometimes I call this the PQ form. And then depending on A being positive or negative, if A is positive, then my parabola didn't flip vertically and my vertex is giving me a minimum point. If A is negative, then at some point in my sequence of transformations, the graph flipped vertically. I have a parabola pointing down, and I'm going to have a maximum point at my vertex. Now, the y-intercept is sometimes going to come automatically, but in general, I calculate these intercepts in the same way. For y-intercept, set x equal to 0. For x-intercept, set y equal to 0. And then solve the equation. And solve, and solve. So nothing really changes there. And we saw in the example. Sometimes I get a y-intercept for free, maybe an x-intercept, who knows. It really depends on the transformations themselves in the sequence. Any questions so far? We do these things so that if you have any uncertainties more than we cover, you can go and look at your precalculus book. There's many open books. Go visit Khan Academy or wherever you need to review things and spend the time to do that. We only sort of what's the word? What is the word I'm looking for? Highlight the most important things that we absolutely need moving forward. Things that come up again in various ways, especially in when we do the calculus properly. I want to do problem 1.5, number 5, just because it's a little different, so why not? Number 5. So I want to make any quadratic function you want as long as it satisfies the requirements. And in number 5, my leading coefficient, which is the A, let me name that maybe. Where is that? Here, A. Leading coefficient. There we go. Leading coefficient in 5 has to be -2, and I have a specific vertex. And those things are all the things that I see in my standard form. Let me just go to my new page here. What's this line doing here? Be gone line. Okay, so I have leading coefficient, which is A, which is, I just read it, -2. And we have our vertex, which is, I don't remember anything apparently, -1, 2. So, standard form, or PQ form, y equals ax minus p squared plus q. It's always minus here. So that if p is a positive number, then the replacement transformation to x minus that number is shift to the right, which makes it convenient that the vertex coordinate is exactly that p if I have it as x minus p. So I really just fill everything in. -2 for a, -1 for p, 2 for q. So we have, in this case, y equals -2 x plus 1 squared plus 2. And we see the x plus 1 would have shifted it to the left, creating the vertex at axis of symmetry, -1. Done. Easy. Now, there's some variety in problems 1.5 and 1.6 that we can't all do, but we will after the next little bit. And the next little bit might take us into tomorrow, because not everyone remembers it perfectly. So let's continue, unless there are some questions at this stage. Admittedly, it is review, and I will say again at this stage while I'm thinking of it, this kind of course where we start very slowly with familiar things, hopefully, this kind of course sort of lulls you into a false sense of security, that you think, oh, this is super easy. I remember most of this. I don't have to study at all. And then you do that. You think you do that for the whole course. But eventually we're going to get to some new stuff. And at that stage, if you don't study, it's going to be bad times. So the amount of effort and time you need to put in needs to be adjusted as the material, the topic requires. It changes through the course. So we'll hopefully get to something a little bit more challenging. Okay, so I want to look at problem 1.6, number 4, just as an example. So I'll just do an example here. It's not the problem itself. We had, I'll just call it y. I don't care. -2x plus 1 squared. Whoop, that is an ugly x. Wow. I apologize. So we had our standard form. Standard form. If I now simplify this, I will get -2. Let's simplify the bracket. Hopefully everyone can remember how to simplify a two-term bracket squared. First one squared, product of the two times 2, last one squared, and then I still have my plus 4. Then I'll multiply the -2 in to get -2x squared minus 4x minus 2 plus 4. And then I'll merge the constant terms into a single constant term like so. And then we get what we call the general form. General form has the general form ax squared plus bx plus c. The a is still the same as the standard form's a. So there is something carried forward, but the b and the c are combinations of p and q and a in the simplification process. So I have different forms. So the standard form is certainly super nice because I see the vertex coordinates. The a is telling me how the shape, the basic quadratic parabola shape changed. Did it flip? Did it stretch? So it's all right there. In the general form, not so much. A little bit of it in the A is still there, visible, but the B and the C, it's not directly usable to know what happened to the graph. And the unfortunate thing is, just like for linear functions, if I have it in y equals mx plus b form, great. Those constants definitely mean more directly, but it's not always going to be in that form. So the issue is, let me just turn my page here to not miss what I wanted to say. The issue is, let me write it down. Issue, and it's an issue. How do, sorry, multiple things happening in my head. How do we go from the general form back to the standard form? Standard form is nice, right? I see the transformations. If I have it in standard form, I can see my chain of transformations, I can make it, I can manipulate the graph. Everything is super nice. But if I'm given a quadratic function in this general form, how do I sort of reverse this simplification to get back to the standard form? That is the issue now, and really the only issue that remains. How do we do that? That method that we'll use is called completing the square. Now, many people remember completing the square as something they have heard before, but that's pretty much where it ends. Not that you haven't done it, you simply may have found it quite unpleasant, and as a result, you blocked it out, and it's just not in your memory. It was a traumatic experience. You blocked it out. And I don't blame you. It's a little less pleasant than simplification. We have to try and reverse engineer this to try and see the standard form, which we need to make our chain of our sequence of transformations. So before we go into this method, is everyone at least clear on what we're trying to do? Given this general form, how do we make it look nice so we can see the transformations? That is our goal. All right. Now let's do it. I have 1.6, number 3 as the one I want to do. 1.6, number 3. Oops, that one. All right. So there's no issue if I'm able to get it in standard form, right? Because then I just do exactly the same as this, as number 4. I make my sequence of transformations. I see how the graph changes every time. The X and the Y intercepts are pretty easy. Everything's great if I have it in that standard form. But if it's presented as, what is it presented as? Maybe let's go look. Number 3, x squared minus 2x minus 8. X squared minus 2x minus 8. Before we can have all those nice function graph transformations to figure out what's happening to this guy, I need to make it look appropriate. So let's do it. All right. So now please ask me if you don't remember this or if I do something. We'll do a couple of these for sure. This is really kind of scheduled as tomorrow's topic, but why not get a leg up on that and make it a little bit easier for ourselves. All right. So in this case, I don't have to worry about a leading coefficient. It's just a 1. So it's a simpler example than we might see eventually. So let me talk through this, and please stop me if you don't like what I'm saying. I can look at the simplification process up here, and I see that a bracket squared, which is what I'm looking for, when simplified results in 3 terms. There's an x squared, there's something with an x, and there's a constant term. So whether I go forward or backwards, these two groups are the same. The bracket squared is the same as this triple that need to go together to be equivalent to that bracket squared. So I see three things. The problem is they don't all fit together to give me a bracket squared. I don't like this 8. This 8 is bothering me on a personal level. So just stay out of my way, 8. I don't like you. I can't get rid of you right away. So I just don't want to look at you right now. I want something else. I don't know what that something else is going to be, but I know it's not 8. I want something else that would give me some bracket squared. Now I can't just add this question mark value. Then I've changed the function, so I need to take it away again so that everything is still in balance and nothing has happened. Okay, this is my plan. Coming up with a plan for how to figure out the standard form for this function. I know that I need 3 terms, an x squared, an x term, and a number, constant term, to give me a bracket squared. And the bracket squared is going to be x minus something. Let's make it squiggles. He is sent to the timeout because I don't like him. He's offending me. Can't get rid of him. He's still there, but we don't want to look at his face right now. So let me actually not make it squiggles. Let's make it p, because that is what it's called in our standard form. I just need to figure out what should this p be to fit with the x squared minus 2x plus something. Well, if I take my x minus p squared, as if I had it, and I simplify it, it's going to be the first one squared, it's going to be the product of the 2 times 2, it's going to be the last one squared. Let's focus on this middle term. This middle term should be negative 2x. Right? It's right there. I can't change the negative 2x. That is what it is. So what should p be to give me the negative 2x? I have a negative 2 and I have an x, so that means the p should be 1. So let's have this as sort of temporary and continue over here. It's going to have to be x minus 1 squared, so that when I simplify it, I need to get that negative 2x. And the simplification process with an x and a minus 1 will give me my negative 2x. X minus 1 squared will result in the first one squared, product of the 2 times 2, last one squared. So now that negative 2x term is correct. So I have to sort of choose the appropriate p value so that I get the middle x term what it needs to be. Okay, that then tells me that this question mark term has to be 1 as well, because it's this 1 squared. It's really 1 squared. 1 squared needs to be taken away as well. Now the first of the 1 squared, the 1's squared, is in my bracket. It's part of the triple that is equivalent and merge together to give me my x minus 1 squared. This other guy is not there. He's going to have to unfortunately go play with the negative 8. And we'll put them together. We can't get rid of them. They're always going to be there into a simplified negative 9. All right. This now tells me A is 1, P is 1, Q is negative 9. That means I have everything I need. I can now finish it in the exact same way as I did, not number 5. Number 4, make my transformations. Now I'm not going to do the whole thing here. I'm going to do my sequence of transformations without the graph. It's going to start with y equals x squared. it's going to go to y equals x minus 1 squared because there is no significant a to really look at. And then it's going to take that right-hand side and subtract. Oops, not q. 9 and q, not the same. 9. And then everything else is straight forward in terms of what we've seen before. So I'll leave that to you. The important part is how we get to this PQ form, this standard form. Because once I have it, then I can see my transformations, I can isolate them, I can make the sequence, graph, everything's the same. It's when I start with the general form, how do I complete the square to get me my standard form? Now, this is only our first example. Tomorrow we have to do something with an a other than 1, and then talk about how the general form and the standard form are linked in general, and all those nice things. Maybe you remember, maybe you don't. In case you don't, we do spend some time on it. So we'll wrap everything up tomorrow. Everything we need to see. We're doing quadratic functions, but also a little bit more, like these transformations, sequence of transformations, and so on. They will see are applicable to many other functions. So we're doing a little more than just the quadratic function to make our lives easier for the next section after this. But we do have to finish our quadratic function and this completing the square before we can move on and add more basic functions to our library. Some you have seen before, probably all of them, but we want to look at them in a specific way, and maybe it's a way that you haven't quite done or remember. Any questions before we end our lecture for today, or any comments?